after the completion of the second instruction cycle, the CPU will start another one, the third instruction cycle, in this case to execute the third instruction in our program. Now, when that cycle starts, our program counter has the value 100 or decimal 4, which points to the third instruction in our program. So, as in the previous case, the first part of the third instruction cycle will also be an instruction fetch cycle or code fetch cycle. So, to do that, the control unit will put the address of the program counter into the address bus and then initiate a memory read cycle. So during this read cycle, the instruction opcode, which is stored in the memory address 4, will be sent through the data bus and will be loaded to the instruction register. Now this instruction is load A, C, which means that to copy the value of register C into register value A. So unlike in the previous two instructions, this instruction does not need an additional memory fetch cycle to get the data, because both source and the destination address are already in the CPU. Therefore, the control unit can handle this operation completely within the CPU by enabling our source register, which is register C, to send the value to its internal data bus and then asking register A, which is the destination, to copy that value into itself. However, if you look the diagram carefully, you will see that there is no direct path from register C to register A. So the value has to be sent through the ALU, where both registers are connected. But in this case, unlike in the things that we discussed in the ALU operations in the last lesson, here the ALU will not do any processing. It will simply allow the value to pass through itself from register C to register A. So therefore, to accommodate this operation, the CPU has to carry out three different signals. Therefore, to carry out this operation, the CPU has to generate three different internal signals. The first one would be to tell register C to open its content to the internal data bus. And then it has to tell the ALU to allow that value to pass through the ALU without any processing, of course, to its output, which is connected to the register A. And finally, it has to send a signal to register A asking to copy that value and store it on itself. So at the end of the third instruction, we will have the contents of register C now being copied to register A. In addition to that, and similar to all the other instructions, the first part of this third instruction cycle, which is the instruction opcode fetch cycle, has also updated the program counter to point to the next instruction. So in this case, our load instruction occupied only one memory location in memory. So it is updated once by adding 1 to the existing value, and now it holds the value 101 or memory address 5, which is the next instruction in our program in the memory. At the commencement of the fourth instruction cycle, we will have the program counter holding address 101, which is equivalent to decimal 5. In our program, that is the fourth instruction included in the sequence. So as same with the previous operations, the first part of the instruction cycle would be to fetch the opcode itself. For that purpose, the control unit will enable the content of the program counter to the address bus and then initiate the memory read cycle. So the value that comes through the data bus will, in this case, will be loaded to the register instruction register and for control unit to decode thereafter. So when decoding this instruction, the control unit will realize that it's a add operation which involves the ALU. Furthermore, it is adding two registers, internal registers of the CPU. So therefore, it does not need to bring any data from memory. So therefore, to complete the add operation, the control unit will generate the necessary signals. The first would be sending a signal to register B, asking it to enable its output on the internal data bus, which is connected to one of the ALU inputs. The second would be asking register A to enable its value to the other input of the ALU. And then thirdly, the CPU control unit will send a signal to the ALU asking to activate the addition circuit, which will add the two inputs and produce the results on the ALU main output and the status on the flags output. And finally, the controller will send another signal to register A asking it to copy the value of ALU output into itself. In this case, the result will be copied to register A, and the addition of the two values does not result any overflow. So therefore, the overflow flag or the carry flag in the flag register will be set to 0. So at the end of the fourth register, we will have also the program counter updated again to point to the next instruction in the sequence, and also the results of the addition available in the register A and the status of that addition available in the flag register. After completing the fourth instruction, we have our program counter updated to point to the fifth instruction. So at the beginning of the fifth instruction, in the same way as all other previous instructions, the control unit will execute the fetch cycle to bring the opcode of the instruction itself into the CPU. For that purpose, it will send the value of the program counter through the address bus to the memory and initiate a memory read cycle. So after completing this memory read cycle, the value that comes through the data bus, which is the instructions opcode, will be stored in the instruction register. Our fifth instruction is slightly different from the previous instructions. Why? It will execute a memory write cycle to store a value which is in the in a register, in this case register A, back into the memory. Now for that purpose, it needs to also need to know an address of a memory location in which this data value has to be stored. And in this particular instruction, that address is available on the memory location immediately following the instruction. So the control unit will realize this information when it decodes the instruction which is now available in the instruction register. And also the program count is also updated by incrementing by value 1, so that it also points to the byte or the location following the instruction. So at the beginning of the instruction execution cycle, the control unit will do another memory read cycle to get the address of the memory where the value has to be stored. For that purpose, it will use the content of the program counter, which is updated now, to address the memory and execute a memory read cycle. So that will cause the content of the memory location following the instruction opcode to be read back into the CPU. But unlike in the previous case, the CPU is not going to treat this as a piece of data, but instead it will treat that as an address of another memory location where it's going to do the write operation. So as a result, it will not store the value read through the data bus in one of its internal registers, but instead it will send it back to the address bus to the memory again to initiate the memory write cycle. So the value that was read just before that will be used as an address in this case. So after putting the address in the address bus, it will send another signal to the register A asking it to enable its content on the data bus. So the value of the content of register A will now become available in the internal data bus followed by the external data bus of the CPU. Then the CPU control unit will generate another signal to memory asking it to copy the value on the data bus on the address specified in the address bus. So once that is completed, we will have the content of the register A, which in fact is the sum of the addition that we carried earlier, being stored back in the memory location specified by the store instruction. So at the completion of the fifth instruction, we will have the content of register A stored back in memory, and also the program counter again updated to point to the next instruction or the sixth instruction in our program. So the address of the program of that instruction will be updated in the program counter register. Now let's look at the last instruction or the sixth instruction in our program, which is a jump instruction. Now the jump instruction is very specific because it will change the order in which the instructions are executed. Normally, as you have already seen, the CPU will always execute the next instruction available in the memory address space after completing the previous one. So it will go sequentially according to the memory address space. But when you execute a jump instruction, it can deviate from that order and jump to a very specific location provided by the jump instruction as one of its operands. So in this case, if you look at the program, you will see that that address is 0100. So if you look at the program listing, in that's one of the instructions that we have executed earlier. So jump to somewhere middle of the program, and that instruction at that particular address will be the add instruction. So again, after executing this jump instruction, the CPU will jump to the add instruction, again start executing from that point onwards. Into that loop, it will again come to the jump instruction and it will again jump back to the add instruction. So in fact, this program is running in an infinite loop, keep on adding the register B with register A and storing that result in the specified location. If you look the program carefully, you will understand that. Now, like in all the other instruction, jump instruction will also start a instruction fetch subcycle at the beginning of the instruction cycle. Now, to do that part, the control input will use the address stored in the program counter, which is updated now to show a point of the jump instruction, to address the memory and initiate a memory read cycle. So the read cycle will fetch the opcode of the instruction and then store it in the instruction register. Thereafter, the CPU will decode this instruction and realize that the controller will realize that it need to find the target destination address of the jump instruction, which is available in the next immediate byte following the opcode. So it will execute another memory read cycle using the current address, which is now being updated in the program counter to address the memory and read the destination of that jump target. So when that value is read through the data bus, now it need to update the program counter so that when the jump occurs, when this instruction is finished and when the CPU looks for the next instruction to execute, the program counter will be having this destination address as the address of the next instruction, so that the execution will continue from that specific address. So the value that you read from the data bus in this case will be stored in the program counter, or it will be used to update the program counter so that the next instruction will point to the destination of this jump instruction.